So a lot of chapter 2 talks about early chemists, the history of chemistry and how that comes about. There are some names that are really important that we need to know about, and I'll make sure to highlight those names. Now, Democritus is one of those names that we really want to know. He was a Greek scientist. He was actually a Greek philosopher, and he's the one that coined the term atom, which he actually called atomos. Now, what he said an atom was a small, indivisible particle. So what he thought would happen is if I took a substance, so if I took gold and I cut it in half and cut that in half and kept cutting, eventually I would get to something so small that it couldn't be broken down any further, and that was an atom. Now, he thought that all atoms for a substance were specific to that substance. So he thought gold had gold atoms. He thought cheese had cheese atoms. He thought that the grass had grass atoms. So he didn't actually know about elements at that time. He just hypothesized that that was as small as we could get. Now, he was a philosopher. He did not do any experiments to prove that atoms exist. He just came up with this concept. Okay? Now, the law of conservation of mass is something that's going to be really important throughout this course. It was discovered by a guy named Lavoisier, French chemist. Now, what he said is that mass is neither created nor destroyed. So in a chemical reaction, I'm not actually creating or destroying atoms, I'm just rearranging them. I'm partnering up with new things. So if I start with 10 grams of reactants at the beginning, then my products should have 10 grams as well. They can be different states, they can be different substances, but they have to be the same mass when they're all combined. Okay? Joseph Proust came up with the law of definite proportions. Now, what he said was that a given compound always contains the same proportion of elements by mass. So he was looking at the ratio of masses of elements in compounds, and he said that it's a set. So if I have water, it's always going to have the same proportion of hydrogen to oxygen by mass. If I have carbon dioxide, it's always the same proportion of carbon to oxygen by mass. Okay? This is different than the law of multiple proportions. Now, the law of multiple proportions says that when two elements form a series of compounds, they do so in small whole number ratios. Now, here's the concept. Definite proportions is looking at a single compound. So water always has the same proportion of hydrogen to oxygen. Multiple proportions is a series of compounds. So for example, I can have NO2, I can have N2O, I can have N2O4. But those subscripts always have to be whole numbers. Okay, so those are how those two things are different. Now, Dalton's atomic theory is really important because it was the first time that we actually really looked at how atoms are the same, how they're different, how they combine. So Dalton came along and he said that our elements are actually made up of tiny particles called atoms. He said that the atoms of a given element are identical. What that means is every gold atom is identical to every other gold atom. Every hydrogen atom is identical to every other hydrogen atom. He said also that the atoms of different elements are different. So a gold atom is very different than a hydrogen atom. Now, we now know that this is not completely accurate. Every gold atom is not exactly the same. We're going to talk about something called isotopes later, but isotopes are two atoms of the same element, but they're slightly different, okay? So this one isn't 100% true, okay? He said that chemical compounds are formed when atoms of different elements combine with each other. And he said that a given compound always has the same relative numbers and types of atoms. So water is always H2O. Two H's, one O, so the same number, and it has to have the same types. I can't have water without hydrogen and oxygen, okay? He said that chemical reactions involve reorganization. Nope, let's try this again. Reorganization, there we go, of the atoms. So again, I'm not creating or destroying matter, I'm just reorganizing it. It changes how they are attached to each other, but I'm not changing the atoms. So if I start with hydrogen and oxygen atoms at the beginning of my reaction, I'm still going to have hydrogen and oxygen atoms at the end of my reaction. They'll just be organized differently, okay? So this is Dalton's atomic theory. It's still really helpful for the basis of how we organize chemistry. Then this guy called Avogadro came along. His name's really important, and you'll see it a lot later on in this unit, and then a lot later on in other units. But Avogadro was studying gases, and what he said was at the same temperature and pressure, equal volumes of different gases contain the same number of particles. Now I'm using the word particles. If it's an element, it will have the same number of atoms. If it's a compound, it will have the same number of molecules. But equal volumes have the same number of particles that make up the gas, okay? This is only true for gases. Equal volumes of liquids do not follow this rule, okay? There we go. So J.J. Thomson is a name that we really want to know, okay? J.J. Thomson discovered, or is credited with discovering, the electron. Now it's important to remember that all of these scientists still haven't actually seen an atom. All of these tests are done indirectly because we don't have electron scanning microscopes yet. We weren't able to see atoms until like the late 1980s. So this is all based on experimentation. And the experimentation that J.J. Thomson did, and you need to know this term, is the cathode ray tube experiment. Now, a cathode ray tube kind of looks like a fluorescent light bulb. It has two different ends. It's got a negative end called a cathode. It's got a positive end called an anode. Now it's called a cathode ray tube because it's going to produce kind of like a laser beam. If you look here, you can see the light going through when I run electric current through it. Now the electric current always starts at the negative side at our cathode, and it moves towards our anode, so we call it a cathode ray. Now, these are negatively charged particles that are moving across, and what J.J. Thomson did is he did a series of different experiments with this tube, but what he found is if he took a negatively charged plate or a negatively charged magnet, that these negatively charged particles would move away from the negative plate. If he put a positive plate here, the negative particles would move towards the positive plate. Now, he decided that our atoms have to have electrons. He said the electrons are going to be negatively charged, but he knew that atoms were neutral. So he said that if we have these negative atoms, or sorry, negative electrons, and our atom is neutral, then we also have to have something positive. Now, he didn't know what that positive charge was. He didn't come up with an answer. What he said was, okay, what if we have this whole atom that has this positive charge, and then we just kind of throw our electrons at it so they stick, kind of like chocolate chips in a chocolate chip cookie. Only back then, what they had, instead of chocolate chip cookies, was they had plum pudding. So he called his model the plum pudding model. Okay? So we've got these positive charged atoms, we've got these neutral atoms with a positive charge making up most of it, and then negative electrons scattered throughout. Okay? So J.J. Thomson also came up with a charge to mass ratio. You don't need to memorize this number. It's given to you, but you'll have to be able to work with it later.